Yo guys, what's up? So we will start the review for RareSkills article on zero knowledge proofs as well, like basically Tornado Cash. So this is a very comprehensive article, and I will try to speed run through because majority of the sections we have already learned. So let's speed run through how zero knowledge works. You can understand how Tornado Cash works without knowing zero knowledge proof algorithm, but you know how zero knowledge works, but you must know. Okay. Contrary to their name and many popular examples, zero knowledge proofs prove the validation of a computation, not knowledge of a certain fact. Uh, Zero knowledge prove the validity of a computation, not knowledge of certain fact. They do not carry out the computation, they take and agree upon computation and prove that the computation was carried out, and the result of the computation then determine if the prover really ran the computation and produced the output. Okay, so for example, you can demonstrate you know the prime factors of a number without revealing them using the RSA, which we learned in the last stream. RSA doesn't claim I know two secret numbers in isolation. It proves that you multiply two concealed numbers together and generated the public key. RSA encryption in RSA, you demonstrate you know two secret primes that multiply together to produce a public key. In zero knowledge, you generalize that magic multiplication to arbitrary arithmetic and Boolean operation. Does that multiplication to arbitrary arithmetic and Boolean operation. Once we have zero knowledge operations for operations, we can build up knowledge zero knowledge proofs for exotic things like proving we know the pre-image of hash function, Merkle roots, or even okay. And does not carry out the computation, it only verifies some and so on. Carry out a computation, produce the useful contrary to generate yet another useful contrary to generate but not verify. Okay, so basically it's saying that for decryption you don't need to do the computation itself. You need to do is follow the path, but however for encryption you need to carry out the computation. How could you prove you know the pre-image of a hash without actually hashing the pre-image? Hence the prover actually carries out the computation and creates some known as okay. When you validate RSA, you don't multiply someone else's private key factors to produce the public key. The signature, you just verify the signature and the message checks out. what happens is that when we run a prover, right, so we run a computation on the input and it generates okay, let's just put it in the here. I'll just expand this because we don't, or be maybe better than that. We create, I have like I've made it a habit of putting everything on an array because I kind of like it. I like the simplistic UI as well as the ability to use multiple models whenever I don't understand something. Pretty insane, by the way, how much we have grown in terms of technology, overseeing how powerful these models have become. Okay, the competition are probably yeah, so I do understand, but I don't wanna, like, I really want to be sure that my understanding towards this is correct. So Tornado Cache is a smart contract mixer that ensures anonymity by decoupling deposit and withdrawal addresses. A user deposits current cryptocurrency after after generating a commitment. Okay, a hash of two secrets, nullifier and secrets that we know, which basically is like so a hash is basically, so the commitment is basically a hash of nullifier and secrets, and the nullifier hash is basically the hash of nullifier, and secret is kept secret all along. This commitment is added publicly to a Merkle tree. For withdrawal, the user creates a zero knowledge proof. This proof verifies that they know the commitment's pre-image and that the linked nullifier hash has not been spent. Or without revealing the secrets. It is okay. Fair enough. Let's understand the prover runs computation and generates ZK. It's sending input. Given only the proof, a verifier cannot. Given only the proof. Okay, so given only the proof, a verifier cannot calculate the public output. The verification step does not conduct calculation. It only verifies that the claim calculation that produced the public output based on the proof, which is basically they are verifying whether the commitment that the user has shared is a part of the Merkle tree or not. So the biggest question or the biggest problem that zero knowledge proof is solving is that we don't want other peoples to know which commitment belongs to me, and that is how Tornado is working. That whenever there is a Merkle tree, whenever you try to withdraw, you just like you don't, like people cannot predict um, which commitment ID your transaction belong to. Yeah, fundamentally tokens, Tornado Cash, anonymization, mixing. This is so the deposit is public, but the withdrawal is also public. What isn't public is that the two addresses involved are associated with each other. Okay, all people can tell about this address card. So the biggest question I would like, the biggest problem so this article is all about how the code is implemented, but the magic piece, which is like the calculation, right, is not going to be discussed in the article. So but this is, and of course I'm really happy at the same time that we don't have to deep dive into the magical implementation, how zero knowledge works. But that's that will be amazing if I could understand that. So soon, like someday, maybe I'll try to discuss it. yeah, sorry. So like this is interesting line here. It's saying that, however, like in some way, if the withdrawer can demonstrate, they know the pre-image, like which is the previous, the original data of one of the hashes without revealing which hash it is. Like, okay, this is basically saying that, okay, this is the pre-image, right? I have this proof that this is basically a pre-image of one of the hashes, and I cannot tell you which hash it is, and also without revealing the pre-image of the hash, like what is the pre-image. So basically there are two things here. One of the like two things here. First of all, uh, the prover, right, or the person uh, that is trying to withdraw cannot reveal that what is the pre-image data of the hash, which is like the original data of the hash, and it cannot also tell that which hash is the pre-image and like does belong to. So two things. So let's write it down. Okay, so we expect the user of a tornado cache to not provide the pre-image of the hash, also not provide the information on which hash we know about. Yeah, so this is the two requirements that we are trying to solve here, that we want to redeem, but we cannot we cannot tell you uh, like I want to tell the prover that I know the pre-image of one of the hashes that you have, right? But I cannot tell you what the data is and which hash it is. Yeah. So I can basically it's just proving that one of the commitments that you have belongs to me, but I cannot tell you which commitment. Also, what data does it have, right? So simply put together, this is that. The naive solution to this is to create a computation where we go over hashes in a loop. Okay, one sec. So the naive solution, okay, here it is to create a computation where we go over the hashes in a loop. not pretty sure how does like what is logarithmic. I have read it, but I can't recall it. So we'll like put it late, like we'll understand it later. But so far, what we have said is that instead of looping over the proof itself, so the prover does not actually do any computation. The only thing that the prover expects is that a proof where it mentions that okay, I like the user is basically saying that I know one of the proofs that is in within your data structure, which is Merkle proof, and and I know the pre-image of that, right? But I don't want to disclose which commitment uh, and the secret, but only that okay, I have like I know, but like I'm claiming that I know one of the commitments pre-images. And then we are talking about Merkle tree. So if you haven't uh, if you don't know much about Merkle trees, you can just check out the yesterday's stream where we learned about Merkle trees. So yeah. When cryptocurrency is deposited, the user generates two secret number, concatenates them, hashes them, and puts the hash. Okay, which is like basically the nullifier and the secret. At withdraw time, the withdrawer produces a leaf hash pre-image. At withdraw time, the withdrawer produces a leaf hash pre-image, which is like the I think there's the leaf hash pre-image is basically okay. So yeah, but the interesting thing about it is like the problematic thing is so the current like so if so what it is saying that if in the withdrawal time we produce the leaf hash pre-image, like basically we create on top of like the original pre-image, then the hash is like to prove whether the hash like we compute the pre-image, and because since we know the pre-image data, uh, this of course, but if we do the Merkle proof and the leaf pre-image verification in zero knowledge manner, then we cannot link back. Okay, zero knowledge proofs let us prove that we generated a valid Merkle proof against the public Merkle root. Zero knowledge proofs lets us prove that we generated a valid Merkle proof, which is like whether the leaf exists within the Merkle root or like within the Merkle root or not, as well as the pre-image of the leaf without showing how we conducted the computation, which is cool. It is not secure enough to simply provide a zero knowledge proof of having Merkle. It is not secure enough to simply provide a zero knowledge proof of having a Merkle proof and of having okay the Merkle. Okay, so it's not just that they have to provide the Merkle proof of the existence, but they also should provide a the zero knowledge proof that they know the pre-image data, right? This is right. It is not secure enough to simply provide zero knowledge proof of having a Merkle proof and producing the root. Okay. The Merkle tree is fully public. Anyone can compute any of the leaves. Correct. Therefore, providing a leaf in the tree is not sufficient to prevent theft by forgery. The withdrawer must also provide proof of knowledge of the pre-image of the leaf in question without revealing the leaf itself. So the withdrawer must prove that they know the pre-image of a leaf in question without revealing the leaf. Remember, the leaf itself is the hash of two numbers. So basically it's saying that we want to provide a proof. So like, okay, it's getting very confusing. So understand it in a way that we want to provide a proof, but we don't want to tell which commit ID we are referring to, right? And we know the pre-image, what are the pre-image data. So what it is saying that the withdrawer must also provide knowledge of the pre-image of the leaf in question, which is like, okay, without revealing the leaf details about the leaf. Okay, this data belongs to this leaf, we don't want to tell. You can see that the commitment argument, you can see that the commitment argument in the function for deposited public, the commitment variable is the leaf being added to the tree, which is the hash of the two secret number which the depositor, okay. Effectively, the proof for withdrawal consists of the following computation. Effectively, the proof for withdrawal consists of proving following computation has been carried out. We provide Merkle proof, the hash of secret 1 and secret 2, the numbers that we want to proof, and the hash, and we do something that basically, okay, takes the Merkle proof. think it needs to like when we are withdrawing, right, the user, we expect the user to pass a nullifier like the commitment ID and the neighboring pieces, right? So what we are like doing is we are not asking the user to pass the commitment ID, but the hash of the the actual hash of the nullifier, and that will like, and the proof itself. So we don't link the commitment ID to the user, and we calculate it on the fly. So we have read about like the quick overview about what are the expectations and what are we passing and how it is supposed to work. So let's understand the other pieces of the puzzle, which is like the nullifier scheme, etc. The scheme above has an issue. What prevents us from withdrawing multiple times? Presumably, we'd want to remove the leaf from the Merkle tree, but that would reveal which deposit is ours. Correct. Tornado Cache handles this by never removing the leaves from the Merkle tree. Once the leaf is added to the Merkle tree, it stays there forever. Also, if we do remove it, we need to update the hash. So it is like an added like an add up cost. So to prevent multiple withdrawals, a nullifier scheme, which is quite common, a nullifier scheme in zero knowledge behaves like an exotic nonce that provides layer of anonymity. I don't think so. It is clear why there are two secret numbers that make up a leaf rather than one. The two numbers that go into the deposit hash are the nullifier and the secret, and the leaf is the hash of the both of them in that order. During the withdrawal, the user must submit the hash of the nullifier, that is the nullifier hash, and prove they concatenated the nullifier and the secret. Okay. Okay, so this is interesting. Oh my god, what the fuck? Can I change the color, please? Yeah. So the user needs to submit the hash of the nullifier and the proof that they can like concatenated the nullifier and the secret. That is the proof that the user needs to pass, and hashed. Okay, and hash that to produce one of the leaves. Okay, basically So the nullifier hash is added to the mapping to ensure it is never used. This is why we need two secret numbers. If we read both of them, know which very interesting. You may have noticed. So I think that depth is 1, 2, 3, but these are 2, 3. Do they refer like this, or how does it work? Yeah, I think this should be the one. Like 1, 2, and 3. This can hold up to 8 leaves. Which is 1, 2, 3, 4, 5, 6. No, 1, 2, 3, 4, and 8. Okay, so it can 8 leaves. So we want, like, basically the leaves will be the downwards. Okay. So basically a fixed depth of 32, which that means it cannot hold more than to the power 32. Okay, I have to cut off the stream because I need to go out. But when I come back, we are going to study again from here till the end. And I'm gonna take a lot of notes here because I think I'm quite confused. But to summarize, what we have learned so far is that we there are two inputs that the smart contract is expecting. Or basically, let's start from the the encryption first, right? So first of all, we generate two values, which is like the secret as well as the nullifier, right? Which basically bounds towards a pre-image data, right? So we are basically signing some data, right? And no so, they are basically commitment IDs, right? So we are committing. Okay, so when I am depositing, I need to provide a commitment ID. Okay, this is my commitment. Then this is my deposit of the this commitment ID, um, and just deposit it, right? So when I, as an withdrawer, I cannot be linked to the commitment ID, so I don't want to disclose my actual commitment ID. So I don't pass my commitment ID, but rather I pass the one of the secret inputs, which is like the nullifier, but it's hash, not the actual nullifier. So what happens is that the I provide the ZK proof that okay, this is, I know the pre-image of one of the leaves within the Merkle tree, and this is the nullifier hash that I that this is one of the elements of that commitment. So I don't want to disclose which commitment it is, but just look into it that I am verifying it, right? So this is what we are doing in zero knowledge, but we are trying to understand like how does Merkle tree comes into picture. And I hope you liked my explanation, and I'm gonna see you soon. Ciao.